Ladies and gentlemen, good evening. Thank you for joining the Shaw Prize Lecture on Mathematical Sciences 2021. I'm Professor Ngai Ming Mok from the Department of Mathematics of the University of Hong Kong. Today, I serve as a moderator for the lecture. As an international award established under the auspices of the Sir Run Shaw Foundation in 2002, the Shaw Prize honors individuals who have recently achieved distinguished and significant advances in academic and scientific research. It consists of 3 annual awards: the prize in astronomy, the prize in life science and medicine, and the prize in mathematical sciences. In 2021, the Shaw Prize in Mathematical Sciences was awarded to Professor Jean-Michel Bismi and Professor Jeff Chiga for their contributions to the development of modern geometry. Talking about the basics of modern geometry, what is the first thing that would come up in your mind? Yes, of course, manifolds. A manifold can be thought of as a higher dimensional generalization of the notion of a surface in 3-dimensional space. Manifolds are ubiquitous in mathematics and physics, and their study has led to remarkable developments. One of these developments is the fact that global topological quantities of a manifold can often be computed using local tools by integrating a local quantity, the curvature, over the surface. In 1963, such an idea was vastly generalized by Atiyah-Singer index theorem, subsequently leading to an entire subfield of mathematics devoted to index theory. Professor Jean-Michel Bismi played a central role in index theory. Earlier, he made profound contributions in probability theory that have had a major impact on mathematical finance. He later imported ideas from probability into index theory, reproving all of the main theorems and vastly extending them. This enabled him to successfully link index theory to other parts of mathematics, like Arakailov geometry, which is used in number theory to study high-dimensional Diophantine equations, and to physics. Tools developed by Bismi have been used to compute the genus 1 Gromov-Witten invariant. In recent years, he has been changing the way that we think about the Selbit-Trace formula, a fundamental tool in representation theory and modern number theory. Professor Jeff Chiga made his significant contributions in understanding the impact of curvature conditions on the structure of manifolds. For example, Grigory Paraman, a famous Russian mathematician, made essential uses of his work in his solution of the Poincare conjecture. To recognize his impacts in combinatorics and theoretical computer science, an important quantity in graph theory is named after Professor Chiga as the Chiga Constant, which is a numerical measure of whether a graph has a bottleneck. He related it to the first non-trivial eigenvalue of the Laplace-Beltrami operator on that manifold. This has played a central role in the study of random walk in graphs and a subsequent development of profound algorithms for random sampling, integration in high dimensions, and many other applications. The collaborative results between Professor Bismi and Professor Chiga lied on their extension of the eta invariant from manifolds to families of manifolds. This allows them to compute explicitly the limit of the eta invariant along a collapsing sequence of spaces. Unique insights from our Schur laureates have transformed and continue to transform modern geometry in contemporary age. Professor Bismi and Professor Chiga, thank you both for your relentless effort on enriching humanity's spiritual civilization. Before inviting our Schur laureates to share their insights on mathematics, I would like to briefly introduce their academic backgrounds. Born in Lisbon, Portugal in 1948, Professor Bismi is currently Emeritus Professor from Mathematical Department of Université Paris-Saclay in France. He graduated from École Polytechnique and finished his PhD in mathematics in 1973 at the Université de Paris 6. In 1970s, he was an engineer at the Corps des Mines in France for 6 years and became a lecturer at École Polytechnique in 1975. He worked at the Department of Mathematics of the Université Paris Sud since 1976. Now he is a member of the French Academy of Sciences. On a personal note, Jean-Michel and I were actually formerly colleagues at Université de Paris Sud in the early 1990s. In the upcoming lecture presented by Professor Bismi, he will review elementary properties of the hypoelliptic Laplacian. If X is a compact Riemannian manifold, the hypoelliptic Laplacian is a family of differential operators acting on the total space of the tangent bundle, script X, that interpolates between the Laplacian of X and the vertical and the vector field of Z on the script X, the generator of the geodesic flow. The dynamical system, a counterpart, is an interpolation between Brownian motion and the geodesic flow via the Langevin dynamics. This interpolation may preserve the full spectrum of the original Laplacian. Professor Bismi will describe the case of the circle in details and explain connections with the Selbst trace formula and applications to complex Hermitian geometry. So now let us join Professor Bismi's lecture on the hypoelliptic Laplacian.
Okay, so I will speak about the hypoelliptic Laplacian. So the hypoelliptic Laplacian is an object which kept me busy for a very long time now. It is a construction that involves differential operators acting on manifolds. I will give, in the course of the lecture, simple examples of differential operators, but it also has a dynamical counterpart involving Brownian motion, geodesics, and so on. So I will illustrate the properties of this operator in the simplest case as possible and also outline some applications. So here's a summary of my talk. So first of all, the Laplacian and the heat equation. So I give myself X to be a compact Riemannian manifold. So if you don't know what Riemannian manifolds are, you may as well assume for yourself that you take something like R3 or R4 or even R2. Now, on a Riemannian manifold, there is a differential operator of order 2, which is a Laplacian. That's an elliptic differential operator on X. That's the most standard sort of differential operator. And here is an example. In the case of Rn, the Laplacian on Rn is just the sum of the square derivatives. This is an example of an elliptic differential operator. So associated to the Laplacian, there is a fundamental equation of mathematical physics. That's the heat equation. So the heat equation describes the propagation of heat. It's a so-called parabolic differential equation, to the heat operator exponential of the Laplacian T over 2, there is an associated heat kernel Pt of x and x prime, which describes the propagation of heat at time t from position x to position x prime. Now, let me explain briefly what Brownian motion is. Brownian motion was first observed by Brown in 1827. Einstein made the statistical physics theory of Brownian motion in 1905, and the mathematical theory has expanded enormously. So Brownian motion is the most irregular random path possible. In this case, I will look at Brownian motion on a Riemannian manifold. And you can think of it as a path whose speed jumps constantly and whose speed more or less is distributed like Gaussian. So all the speeds are mutually independent, and they are Gaussian, and what complicates the theory a bit is that these speeds are infinite. So there is a basic connection between the heat kernel and Brownian motion. Given x in the manifold large X, if you start your Brownian motion at position little x, then Pt of x prime dx prime describes the probability distribution of Brownian motion at time t. And here is a picture of Brownian motion. It is a big mess. That's probably the picture that mentally Brown was observing in 1827. Now, a last trajectory, which is well known, these are the geodesics. So the geodesic is a solution of a second order differential equation, x double dot equals 0. That makes also sense on Riemannian manifolds. A geodesic is a path which has constant speed, that the most regular path as possible. You can, instead of writing it as a solution of a second order differential equation, you can write it as a solution of first order differential equation by moving to phase space. Phase space is just a space of x, y, where x is in the manifold and y is in the tangent bundle at x. So you wrote it as a first order differential equation, x dot equals y dot equals 0. So that means that geodesics are themselves integrals of a vector field z, which I wrote in the form sum of yi d over dxi. That's the so-called geodesic vector field. And here is a picture of a geodesic, a straight line, very regular. So what is the main statement in my talk? So the main statement says that there is a family of hypoelliptic operators LBX. So hypoelliptic, I will briefly say at some point what that means. So the operators LBX are differential operators still acting on phase space in this space X script. And this family interpolates between the ordinary Laplacian on the base manifold for b equals 0 and the geodesic floor, the vector field z, for b equals infinity. So what means hypoelliptic here? Hypoelliptic means that it's below elliptic and it is almost as good as elliptic. So if you don't know what elliptic or hypoelliptic operators are, what this means is that these operators can be mathematically handled as well as elliptic operators, as well, say, as the Laplacian. What is the dynamical counterpart to the interpolation of differential operators I explained before? So I consider the following equation of mathematical physics introduced by the physicist Langevin in 1908. That's a second order differential equation. It's b squared x double dot plus x dot equals w dot. So in this case, W dot represents random shocks. If you like, that the excitation given by Brownian motion, but at every point in the tangent bundle. Just take it formally as a family of second-order differential equations. And what the theory says is that there is an interpolation of dynamical systems, which is written in the following way. On the left-hand side, you have Brownian motion, x dot equals W dot. That's the formal equation for Brownian motion. Pass x excited by Brownian noise. This is for b equals 0. And at b equals infinity, you get the equation of geodesics. So what the theory says is that indeed such an interpolation takes place. And besides that, it is exactly the dynamical system counterpart to the interpolation of differential operators I explained before. So let me explain how does the hypoleptic Laplacian look like. I took the simplest case as possible. The manifold X will be the circle, so that the total space of its tangent bundle is S1 cross R, whose generic point is written as xy. So first of all, I introduce a differential operator just in the coordinate y. That's a well-known operator in mathematical physics, in quantum mechanics. That's the so-called harmonic oscillator. The harmonic oscillator, it's a self-adjoint elliptic operator, and it's well known that its spectrum consists of the integer. If you have a differential operator, you can think of the spectrum exactly as you would do for a matrix. So the hypoeptic Laplacian is just a combination of this harmonic oscillator, which just acts in the y coordinates, with essentially the vector field y d over dx, which, if you like, in this case, is just the geodesic flow, the operator which is associated with the geodesic flow. It's a weighted combination where the harmonic oscillator has a weight 1 over b squared and the geodesic flow 1 over b. So this operator is also known in mathematical physics. That's a so-called Fokker-Planck operator, which appears in statistical physics. Now, you see well that when b tends to 0, the operator LBX apparently explodes. What the theory of the hypoeptic Laplacian tells you is that in the proper way, it does not explode, and it converges in the proper sense to the Laplacian of S1. So let me now explain how does a solution of the Langevin equation look like. So again, I wrote the solution of the Langevin equation as a second-order differential equation. For b equals 0, we recover our equation for a classical Brownian motion, where the speeds at each time t are mutually independent. The path chooses a different speed independently from each other for each time at each time. For b equals infinity, what you get is the equation of geodesic, where the speeds are constant. They are totally dependent. So you have two kinds of paths, the speeds totally independent and the speeds totally dependent. Now, for Langevin, for the solution of the Langevin equation, the speeds are neither independent nor dependent, they are correlated. I wrote here the correlation function. If you don't know what this is, it's not too important. So why do we construct the hypoeptic Laplacian? So first of all, the deformation preserves subtle invariance, subtle spectral invariance, and sometimes the whole spectrum. And besides, in complex geometry, the hypoeptic Laplacian is better behaved than the usual Laplacian. I will give just one small illustration at the end of the talk. So let's go back to the case x equals S1. In this case, all the mystery of the hypoleptic Laplacian can be unraveled. So I rewrote here the operator LB S1 explicitly. And now what I shall do is that I will take some terms in this hypoleptic operator and I will do a reduction of squares, which is something completely elementary that you certainly know how to do yourself. And then what I shall say is that I will make a change of variables in this reduction of squares. In other words, I will translate the variable y by the operator b over dx. I will make the change of variables y gives y plus b over dx. Now, this change of variables obviously is a non-classical one. What it means actually is that I will conjugate my original operator. If I just think a bit what means this translation, what this means is that I will conjugate my given LBS1 by the exponential of b times the cross derivative. Now, the fact is that this exponential does not make sense as an operator. The operator inside is not an elliptic operator, it is hyperbolic, and so the conjugation does not act on anything. However, if we pretended that it makes sense, what we would find is that because two conjugate operators have the same spectrum, we would find that our operator LBS1 would be isospectral to a new operator now, which is written there, in which the two variables x and y have now decoupled completely, and the new operator is itself elliptic. What this means is that in the two variables, you now have a Laplacian. Now, what the theory of the hypoleptic Laplacian says is that in spite of the fact that the conjugation does not make sense, the conclusions are true. The two operators are indeed isospectral, so that the spectrum of our original hypoleptic Laplacian is given by the term-by-term sum of two pieces. The first piece is n, the integers divided by b squared. That comes from the original spectrum of the harmonic oscillator. And the second term is just a spectrum of the Laplacian on S1. So, as you see, when b tends to 0, most of the spectrum of the hypoleptic Laplacian tends to infinity, and the piece which remains bounded just converges to the spectrum of the Laplacian on S1, which gives already some credibility to the fact that the hypoleptic LBS1 deforms the original Laplacian. Now, let me give some explanation of why the harmonic oscillator is going to appear. Poincaré lemma and the harmonic oscillator. So, let me introduce the de Rham complex on the real line. So this is a very simple object. It's just made of smooth sections of the exterior algebra of R. If you like, it's two copies of the smooth functions of R. It's equipped with a de Rham operator, and it's well known that the cohomology of R is made of two pieces. H0 is equal to R, and H1 is equal to 0. Now, to get the so-called proper Hodge theory of R, if you don't know what Hodge theory is, it doesn't matter. You need to modify the volume form when you construct the Hodge Laplacian by modifying the volume form by a Gaussian scaling. In this case, what you get is a so-called Witten Laplacian. That's a modified Laplacian in the y-coordinate, which is the sum of two pieces. One is the harmonic oscillator, the scalar harmonic oscillator, and the other one is a matrix. It's a matrix which acts like 0 on 0 forms and 1 on 1 forms. And in particular, with this Witten Laplacian, we find that the harmonic objects, which are supposed to represent the first cohomology of R, are now represented by a Gaussian function, exponential minus y squared over 2. So, Hypoeptic Laplacian and Poisson formula. I will just slightly modify my hypoleptic operator LBS1. I will make it act now on 2 copies. Instead of having just one, I introduce 2 copies of the same operator with a shifting matrix N, which is either 0 or 1. So there is then a fundamental identity, which is a consequence of the statements I outlined before. And it says the following, that the trace of the original elliptic heat kernel on S1 is given by the supertrace. Supertrace is just the difference of the traces of the heat operator for the hypoleptic Laplacian. So there is a conservation of a trace on one side to a supertrace, difference of traces on the other side. And this is just a consequence of the evaluation of the spectrum I had given at the beginning. Now, what do you get from this equality? By making B tend to infinity, using the fact that the hypoleptic Laplacian converges to the geodesic floor, you recover a proof of the well-known Poisson formula, which says that the trace of the heat kernel on S1 can be described in terms of the length square of the closed geodesics in S1. So let's go back to Brown for a moment, 1827. So Brown had observed Brownian motion, which, as we know, is a path with infinite speed, but however, Gaussian increments. I said more or less that the speed were independent Gaussians. And the question we're going to ask in a somewhat provocative way is to ask whether Brown was observing Poincaré lemma in infinite dimensions. Can we use Brown's observations by introducing, in some sense, the proper cohomology? So I won't explain what this cohomology theory is, but it's just to give a mathematical justification to what follows. So I will illustrate this by mentioning Selberg's trace formula, proven by Selberg in 1956. So in here, X is just a Riemann surface of constant scalar negative curvature minus 2. And on such a Riemann surface, you can look at the so-called closed geodesics, and let me call L gamma to be the length of such a closed geodesic. Now, Selberg's trace formula is a formula that expresses the trace of the heat kernel in terms of quantities that involves all the possible closed geodesics on the manifold X. This formula was found by a simple computation in the case of Riemann surfaces, and what we will do now is extend this to more general geometric objects. Let me just mention here that the left-hand side involves the Laplacian, the right-hand side involves the geodesic floor, and we will think of such a formula as being obtained by interpolation between the left and the right-hand side using the hypoeptic Laplacian. The coefficients here in this Selberg's trace formula are so-called orbital integrals in the case of the simplest non-compact Lie group SL2 of R. So let me now go to a more complicated geometric space, the case of symmetric spaces. So I consider a symmetric space. So this is obtained in the context of theory of reductive Lie groups, non-compact Lie groups, G mod K. In this case, actually, the theory of the hypoleptic Laplacian is not enough to look at the tangent bundle. You need to add another bundle, which is N, and actually the analysis for the hypoleptic Laplacian takes place on this bigger space. And we will again use Witten's Hodge theory along the fiber of this enlarged vector bundle. So let me state now a fundamental identity that generalizes Selberg's identity, if you like, or the identity that I had given before in the case of the circle theorem. If you take gamma to be a discrete torsion-free subgroup of the Lie group G, and you take Z to be the quotient of X by the discrete group gamma. So this is a way of constructing a compact manifold from the symmetric space. Then we have an identity which is exactly the analog of the one I had stated in the case of the circle. The trace of the original heat kernel on Z is given by the supertrace alternate sum of traces of the heat operator for the hypoleptic Laplacian. By making B tend to infinity, one finally gets explicit geometric formula for orbital integrals. These formula were not known before, and these are similar in their structure to the theorem of Riemann-Roch-Hirzebruch. Now, let me briefly explain the application of the hypoeptic Laplacian in complex geometry, complex manifolds, and elliptic Hodge theory. So let X now be a compact complex manifold equipped with a Hermitian metric. Let me introduce square X, which is a Hodge Laplacian, which in this case acts on the Dolbeault complex, on anti-holomorphic forms on the manifold X. We know that this Hodge Laplacian is just an ordinary self-adjoint elliptic operator with respect to a classical L2 Hermitian product. What is going to be hypoleptic Hodge theory? So first of all, let me explain it in the simplest possible case. I just introduce a Hermitian form on differential forms on X, which instead of being based on the L2 product of the forms, as usual, is just based on their intersection product. I will not explain here the notations, that doesn't matter. By properly scaling this intersection product, what you get for theta, it is a Hermitian form. It is not positive, but it is still non-degenerate and properly symmetric. You can develop a Hodge theory based on the form theta, and essentially what you get is a version of Schoenweill theory, so that the corresponding Laplacian is just the classical curvature in Schoenweill theory. So what is the form of the hypoleptic interpolation in such a case? That's an interpolation between the classical Hodge-Dolbeault theory on the complex compact manifold on one hand and Schoenweill theory on the other hand. And this interpolation in particular leads to a proof of a rather complicated theorem I obtained recently with Suchen and Zouting Wei, proving Riemann-Roch-Grothendieck for coherent sheaves on Hermitian manifolds. Now let me go back to the Langevin equation. In 1908, on R3, Langevin introduced the Langevin equation, which he wrote more or less in the form mx double dot equal minus x dot plus w dot. You will see the original later on. M here is a mass. And the reason why Langevin was doing this, he was trying to reconcile Brownian motion, the theory of Brownian motion with classical mechanics. The question was that Brownian motion, it was already understood at the time that Brownian motion was only possible for particles which had zero mass, because Brownian motion has infinite speed, and if they did not have zero mass, they would have infinite energy. So Langevin was already trying to slow Brownian motion down, so that would describe a random motion of a particle with a mass. In the theory of the Hypoeptic Laplacian, there is a relation between Langevin mass m and our parameter b squared. In other words, our interpretation of b squared now, it's exactly a mass for Langevin. So the hypoleptic theory consists actually in considering classical mathematics with Laplacian and so on with non-zero mass. And here is a picture of Langevin's equation in its original version. You see exactly the equation that he wrote. It's not exactly the same formalism, but almost. So I think it's interesting to see that at more than 1 century of distance, in some sense, for completely different reasons, the same equation pops out. Thank you very much. Thank you.
So thank you. It is a truly inspiring lecture, Professor Jean-Michel Bismi. Thank you so much. Next, we are very glad to have Professor Chiga to share his insight on quantitative differentiation. Professor Chiga was born in 1943 in New York City of the United States. He is currently Silver Professor of Mathematics at the Corona Institute of Mathematical Sciences of New York University. He obtained his bachelor's degree from Harvard University in 1964 and received his master and PhD in mathematics from Princeton University in 1966 and 67 respectively. So after working at the University of Michigan as an assistant professor between 1968 and 69, he joined the faculty of the State University of New York at Stony Brook in 1969. He has been professor at New York University since 1969. He is now a member of the U.S. National Academy of Sciences, American Academy of Arts and Sciences, and the Finnish Academy of Science and Letters. In the following lecture, Professor Chiga will discuss the simplest instance of a notion called quantitative differentiation. More sophisticated instances have played a key role in contemporary advances in the analysis of singularities of solutions to nonlinear partial differential equations, such as the minimal surface equation. The simplest case pertains to differentiable functions, where the only information available is a bound on the derivative, for instance. Although the discussion requires only elementary calculus, it provides a framework for more advanced generalizations. So now please join Professor Chiga's lecture on the quantitative differentiation.
Okay, so I want to discuss the simplest and most elementary case of a principle that's played a role in my work over the past 25 years. The applications have ranged from nonlinear geometric partial differential equations to theoretical computer science. Different parts were done jointly with Toby Colding, Gang Tien, Bruce Kleiner, Asaf Naor, and Aaron Neighbor. Instances of the principle actually had appeared in apparently rather specialized works of Doran Soro, Jones, and David Sems. And I call the principle quantitative differentiation. So the case that I'll present is closely related to one discussed in the paper, really the appendix of a paper by Peter Jones, the analyst's traveling salesman problem. But the proof we'll give is somewhat different. It requires only elementary calculus, but it's not taught in standard courses, and experts seem to not have been aware of the statement. Perhaps as a consequence, prior to our work, potential applications to nonlinear elliptic and parabolic partial differential equations and in theoretical computer science were missed. So let's revisit what it means for a function to be differentiable. So we have a function f, and to say that it's differentiable at a point x bar, it can be expressed as follows. So we restrict f to a small interval of size delta centered at x bar, and then we rescale both the x and y coordinates by a factor delta inverse. So then in the limit, as delta goes to 0, the rescalings of the function f of x minus f of x bar converge, now on an interval of length 1, to the unique linear function f prime of x bar times x minus x bar. Now, I want to emphasize that really what we just said involves two separate conditions, which I'm calling A and B. The first condition is the appearance of special structure on a small scale. Maybe we could say approximate special structure if we like. And then B, when we let delta go to 0, the limiting special structure is unique. Now, what's the main issue? The main issue is that examples show that as delta goes to 0, we can't control the rate at which the rescaled functions converge to f prime of x bar times x minus x bar. Now, remember Taylor's formula, and an immediate consequence is that the difference that we're interested in can be bounded by an expression, the remainder in Taylor's formula, involving the second derivative. So therefore, if we assumed a bound on the second derivative, we could estimate how well the rescalings of f of x minus f of x bar are approximated by the linear function f prime of x times x minus x bar. Okay, but we don't assume such a bound or even that the second derivative exists. So the idea instead is we concentrate solely on quantifying condition A, and that was namely almost linearity. And this turns out to be possible precisely because we're not insisting that the approximating linear function is f prime of x bar times x minus x bar. So therefore, we should be clear that what I'm calling quantitative differentiation is not differentiation in the usual sense, since only condition A is involved. However, let's realize that knowing that a function is almost linear is useful knowledge. So now let's make the notion of being approximately linear, or let's call it epsilon linearity. So we'll use the notation that, let's say, the norm of J, that just means the length of the interval J. And now we let L denote any affine linear function. And if we have a function, we say its restriction, F is the function, we say its restriction to the interval J is epsilon linear if the inf, that is, we take the best L that approximates F, and then sup means this is supposed to hold at all points in the interval. And notice we, of course, normalize by the length of the interval. So we take the best linear approximation to F in absolute value, we normalize by the length of the interval, and if we can choose L so that this becomes less than epsilon, we call the function epsilon linear on the interval J. And let's notice that the condition of being epsilon linear doesn't rechange if we rescale the x and y coordinates, remember, as we did earlier. The next notion we need is that of the dyadic subintervals of an interval. And I denote them in this way. So for each n, there'll be 2 to the nth corresponding dyadic subintervals, each of length 2 to the minus n. And these are gotten simply by taking the interval j and repeatedly bisecting it n times. So we get 2 to the n intervals of length 2 to the minus n. So if we go from n to n plus 1, what happens is we just bisect this interval and we get that it's the union of 2 subintervals of half the size. So in particular, for our interval 0 to 1 that we're denoting by I, then the various dyadic subintervals are given explicitly in this way. And notice that n can have any value between 1 and infinity, depending on how many times we bisect. Also, why are we considering dyadic subintervals as opposed to just arbitrary subintervals? Well, basically it's enough to consider dyadic subintervals because any interval is comparable, any j that is over here is comparable to dyadic subintervals in this sense. So we can find one that approximates it best from the inside, and we only have to expand it slightly to get something that contains it. So we may as well just consider dyadic subintervals rather than arbitrary ones, and that simplifies our discussion. So now here is the main theorem. Here's the one that we want to understand the proof of, but first we want to understand the meaning of it. So remember, for each n, there are 2 to the nth dyadic subintervals. And on the other hand, so they add, their lengths, of course, add up to 1. However, there are infinitely many values of n. And so the sum of the lengths of all possible dyadic subintervals is infinity. Okay, so now here comes the theorem. Theorem 1 is the main theorem. For all epsilon greater than 0 and any differentiable f, we don't care what it is, the lengths of the dyadic subintervals on which f fails to be epsilon linear is finite. And in fact, it has a definite bound, and here is the bound. So the smaller epsilon is, of course, the larger we would expect the bound to be. And what is it being bounded by? We take, this is really what's called the L2 norm. We take the derivative, and now this denotes its average value on the whole interval. We take the difference, so we're looking at the deviation of f from its average value. We square it to get something positive, and then we take the square root. And that is supposed to bound the sum of the lengths, this expression over here, of all the dyadic subintervals on which it fails to be epsilon linear, which means on all the infinitely many that are left, it is epsilon linear, no matter how small epsilon is. Okay? So this is quite striking because the sum of the lengths is infinite, but the failure to be as linear as we like is bounded by a finite constant, namely this one. Okay, so I hope the point is clear. Now, before we go to the proof, let's look at an example. And I learned this example from Stephen Semmes. It's very simple. We take a sine function and we think of k as being large, but it could be anything. So when k is large, this is a function we could say of high frequency but small amplitude. So the 2 to the minus k is in front. Now notice if we differentiate this function independent of the value of k, the 2 to the k comes out and it gets canceled by 2 to the minus k. And so for any choice, this should maybe have a sub k here, the derivative of this function is actually bounded by 1. In fact, for these with suitable rescaling, maybe the length, the average value would be 0 of the derivative, and also of the function for that matter. Okay, so now let's think about what this looks like. In particular, let's think of k as being rather large, and now there are some possibilities for the dyadic intervals that we might restrict it to. So even though k is large, so this is small, so now we would have a bunch of dyadic intervals which, although they also might be short, if k is, say, really large, so 2 to the minus k is really small, then a very good approximation to our rescaled function that interests us is just L is identically 0, and that's because of this coefficient in front, which is going to be very small. Now, on the other hand, having fixed k, if we look at dyadic intervals for which the number of bisections n is comparable to k, so the length of the interval is comparable to 2 to the minus k, then it just looks basically like an ordinary sine function on that scale, and it's not very linear. Okay, so those are going to be the bad intervals we're imagining. It just looks like an ordinary sine function on those intervals. And then when we go below 2 to the minus k in length, indeed it will look like the linear function corresponding to its derivative, the one that we saw before, right? So the interesting thing is, for a long time, if k is large, it won't look like its derivative. And in this transition region, in fact, it won't look very linear. But it's compensated for by the fact that for the longer dyadic intervals, those of length bigger than 2 to the minus k, just the linear function, which is identically 0, works just fine. Okay. Now, in fact, we can easily make this example a little bit better, and this shows that the estimate in Theorem 1 is actually sharp. So namely, we're going to combine capital N of these functions, but we have to be just a little bit careful about how we choose the k's. So we choose the k's now to grow, let's say, exponentially. And then if you think about what happens when we add a bunch of functions up like this, the main point is separation of scales. If the scales grow sufficiently fast, then the behavior on one scale of a function constructed in this way doesn't affect the behavior on the other scales. So on the larger scales, we're restricting to where the function already looks good, linear, and on the smaller scales, even when we add up all of them, it won't affect the values for a given k sub j. So it won't affect the behavior, I should say. So if we're careful about keeping the scales separated, we can just add up a bunch of functions as on the previous transparency, and from that we see immediately, we get a whole interval worth of bad ones for each value 1 through capital N, and this, if you look at it, shows that the estimate that we looked at in Theorem 1 can't be improved. Okay. Now, in order to prove this theorem, I want to prove what you could think of as an even more basic theorem. So we'll have a notion that resembles the previous one of being epsilon linear, but it's even simpler. Namely, it's the notion of being epsilon constant. So, but we'll measure it in a slightly different way. So we have this notion for the average value of the function on the interval j, this notation, I should say, So h sub j denotes the average value of the function h on the interval j. And sometimes I use this notation rather than this. So if the integral has a bar in it, we understand I've divided through by 1 over the length of j. Okay, so now similar to what we had before, but we're using a slightly different measurement, namely the average of what you would call the L1 norm, the interval of the absolute value. So we'll say the function h is epsilon constant if, when we look at the integral of the absolute value of the function minus its average, and then we normalize, as we should, by dividing through by the length of the interval. If that's less than epsilon, then we'll say it's epsilon constant, right? So the deviation in this so-called L1 sense from its average value, suitably normalized, is supposed to be small, where epsilon is a small number. So now what we're actually going to prove is Theorem 2, which is stated over here, that there exists a certain constant c. The proof will show a constant c that works. And the rest of the statement is kind of reminiscent of Theorem 1. It says that, again, although we remember the sum of the lengths of all possible dyadic intervals is infinite, the sum of the lengths of the intervals on which a function h is not epsilon constant has a bound quite analogous to what we saw before. Namely, we look at h minus its average, we square it, that makes it positive already. We divide by the length of the interval when we integrate, and then we take the square root. So this looks like a norm. This is something like the standard deviation of the function. So it's the L2 norm of it minus its average. And the claim is we have an estimate that looks very similar to before. The sum of the lengths of the intervals on which h is not epsilon constant is bounded by a constant times epsilon inverse, and then times this, which depends on the function h. And as before, this is the best possible statement. And then to get Theorem 1 about almost linearity from this theorem, we just look at the case where the function h is the derivative of our function f, and then we apply the fundamental theorem of calculus, that the function is the integral of its derivative with a suitably chosen constant. Okay, so now let's start on the proof of Theorem 2. So the first thing is to notice that if we take the sum of the, I always make this mistake. So we take the sum of these quantities here, notice that occur, but there isn't a normalization yet in the definition of being epsilon constant. So what I have here is the same thing without the normalization. So that's over here, and summed over all possible dyadic intervals. So there are infinitely many dyadic intervals in this sum because I consider a sum both over n and the corresponding index I sub n, which runs from 1 to 2 to the n. And now I've just rewritten it over here by dividing through and multiplying through by the length of the interval. And this is to make manifest a standard fact that if I have such a bound, then I have control of the lengths, the sum of the lengths of the intervals where this is bigger than epsilon, right, in terms of the left-hand side over here, right? Because if there were too many, if the sum of the lengths was too big, where the condition of being epsilon constant would be violated, then I would get a contradiction provided I had a bound on the left-hand side. So therefore, the conclusion is lemma 1, which is basically the standard fact called Markov's inequality, that the sum of the lengths of the intervals on which the bad intervals, the ones on which h is not epsilon constant, is bounded by epsilon inverse times the sum on the left. That's this sum over here. So to complete the proof of Theorem 2, all we have to show is that the sum on the left is bounded by the quantity that appeared in the statement of the theorem. That was this quantity over here. So I'll just go back for a second to remind ourselves, right? So this is the bound that we want to prove, and this is the bound that's almost obvious from Markov's inequality. So to prove the theorem, we have to prove that what's on the left-hand side is bounded by the quantity in the theorem. So really, I should be maybe looking over here, that this, which has the epsilon inverse in it, is bounded by this, which doesn't have the epsilon inverse in it. And then we'll be done, if we can see that. So in order to prove that, I want to introduce a family of functions, which I'll denote h sub n. And it'll really be h sub n of j, where j is any subinterval. I want it to be any subinterval, although of course I'm particularly interested in the unit interval I, which is our basic big interval, right? And so it's very easy to understand what this function h sub n is. I just take one of the dyadic subintervals of j, and I replace h on that subinterval by its average value. And we write h sub n for h sub n of our original interval 0, 1, which I'm denoting by I. So now there are two important remarks. One is that if I'm looking at all possible dyadic subintervals, then a dyadic subinterval, so to say, can arise in two different ways, either because it's a subinterval of the big interval, or because I'm inspecting that subinterval in and of itself. But I have this inequality over here, that the big h sub n restricted to this subinterval is h sub 0 restricted of the subinterval restricted to the same one. And this is just to say that in both cases, it's the average, the value of the function is the average value of h on the dyadic subinterval. The second point we have to take note of is that a given dyadic subinterval is contained in exactly n dyadic intervals. Remember, we keep bisecting. So if we look at that process in reverse, if it has level n, then it was gotten by bisecting an interval of level n minus 1, and that one was gotten by bisecting one of level n minus 2, and so on. And so we see that every dyadic subinterval of level n is actually contained in a sequence like this. So it occurs n times in the sum over all dyadic subintervals. And the value of the function is the same. So we're going to use that now. Okay. So now let's introduce what's a standard way of making the functions on 0, 1, we should say square integrable maybe, into an inner product space. Namely, we define the inner product of the two functions as just the integral of their product. So in particular, if h equals g, it's the inner product is the norm squared. It's the integral of h squared, which is indeed positive as it should be unless h is identically 0, in which case it's 0. Now, let's look at all of the dyadic subintervals as we've been doing. Now, I mean for the big interval. And chi denotes the characteristic function of this dyadic subinterval. So that means, by definition, chi is identically 1 on the subinterval, and it's 0 off the subinterval, just like the characteristic function of any set has that property. 1 on the set and 0 off the set. Now, of course, if the interval is short, then the length in the sense of this inner product of this function will be small. But in fact, if I multiply it by 2 to the n over 2, then I get something of length 1. And of course, if for fixed n, the lengths, the dyadic intervals are disjoint from one another. And so with respect to this inner product, what this gives me is an orthonormal basis for the subspace, which is spanned by these characteristic functions. And since I keep subdividing, that it's easy to see every one that I had before is the sum of 2 at the next stage. So the subspace keeps growing. And because of this remark about these things forming a basis when suitably normalized, if I expand H in terms of this orthonormal basis, I see that what I called H sub n, it's just the orthogonal projection of the original function H on the subspace spanned by these characteristic functions of the dyadic intervals of level n. Okay. And therefore, by linear algebra, it follows that the differences are mutually orthogonal, right? Since this is a sequence of orthogonal projections on a growing family of subspaces. Okay. And from that, we get the basic relation that the norm squared of H minus H naught is the sum of the norms of these orthogonal projections, which is what I've written here. So this is just by linear algebra because these functions, I'll go back, were orthonormal. Okay. So now we can say the following. So first let's look initially at the big interval 0, 1. So just by calculus, the triangle inequality, if you like, the thing that we're interested in bounding, which is the difference between H and its average value, is bounded by this sum. So this is just the triangle inequality, if you like, the fact that the integral of the absolute value is a norm. Now, we can say the same thing, in fact, for any dyadic subinterval. So let's replace I over here by any dyadic subinterval. Well, we would have the same thing. Okay. So on the left-hand side, then we would get this here. But now we use what we observed previously. I'll go back. These two facts, right? So one is whether it occurs as a dyadic subinterval or as some of a bigger interval or one in its own right. The value of the corresponding function h is the same. Namely, it's just hn, or on the left is h naught on the right, because it's just the average value restricted to this dyadic subinterval. And also, we noted that every dyadic subinterval of depth n, let's call it, the depth for now, is contained in precisely n larger ones, which we can think of as its ancestors. And so by using those two facts, 6 and 7, we get that this sum over here, which is over all dyadic subintervals, can be written as something that almost looks like this, except we have to take into account that if the dyadic subinterval has this as n, it's going to occur n times. So this is where we use 6 and 7. And then we'll put the average integral here. This has a bar, and we'll compensate for it by multiplying by 2 to the minus n. Right here we divide it by 2 to the minus n. Okay. And now we're almost done, because consider this product. Let's go back a second. The product that occurred over here, right? So I just want to rewrite it in this way as n times 2 to the minus n. So I write 2 to the minus n as 2 to the minus n over 2 times 2 to the minus n over 2. And now, right, so this is just algebra. And then we apply the Schwarz inequality, right? So this is saying that the integral of the product is less than or equal to the product of the norms. So it's like saying that the inner product of two vectors, the scalar product, is at most equal to the product of the norms. So each of these is, I square something and then take the square root, right? Now, this is a constant, right? Because although n squared is growing, it's more than compensated for by the exponential decrease of this factor 2 to the minus n. So this is just the constant c. And then what I had over here is what I had noticed earlier in 8, we'll go back to 8 in a second, was just a different way of writing the thing that I was interested in initially. Okay, so here is 8, so here is what I had, and then I replaced it by what I was interested in, and now I'm done. So this completes the proof of Theorem 2, and as we remarked, Theorem 1 follows from Theorem 2 by the fundamental theorem of calculus. So, okay, now let's ask ourselves what was really essential about this argument. And if we can abstract what we really used, then you could imagine that it would be useful for generalizations. So really, the essentials are these. These are the three essentials. That we had this quantity, so now I'm thinking of Theorem 2. It's positive, unless it's identically 0, and it can be written as a sum over locations and scales. And moreover, we had an a priori bound on the quantity. That was basically what we assumed in the theorem. Namely, we're imagining we know this over here, right? That comes into the theorem. Sometimes in an application, it might come for some other reason. So there were these two things, and then this is kind of the crucial one. These are in a way more elementary, but you have to recognize that these are essentials that are in play. But the coercivity is the crucial point, and that is that if we can write it in this way, and we have a bound, then the sum of the non-negative quantities being over sufficiently many scales being sufficiently small, then it must follow that special structure must be present. And in our case, in Theorem 2, special structure meant the function looked almost constant, and in Theorem 1, it meant it was almost linear. So let's now sum up. So the applications, the more recent applications, in particular in my work with my collaborators, here are some of the buzzwords or the names to which these general ideas were applied. So the partial regularity theory for Einstein metrics, minimal submanifolds, harmonic maps, mean curvature flow, and also, perhaps surprisingly, a different one, but again, same principles in theoretical computer science. So we should be clear that in such instances, even after finding the relevant energy, the proof of the coercivity, which took a few pages here, could be much more difficult. But in all of these cases, it turns out to be possible. Coercivity meant if the energy didn't change much over many scales, then we must be in the special situation. That can only happen if it didn't change at all. Then we would say the special structure must be present on the nose. And if it only changes a little bit, it tries to improve, but it can't make it, then we must be close to the situation in which there's special structure. We should emphasize that this can be highly non-trivial to prove in the applications, but possible nonetheless. And we should also mention that this is not the only technique, so there are others. I've just given two buzzwords. One is quantitative cone splitting, which is something in the spirit of what we've discussed, and the other is a covering argument. So you might think of somehow a picture like a Cantor set. So you have to recover and recover again a bad set, zeroing in on it. It's just, the point is that, and also to be clear, it's possible in particular cases to give a more refined discussion. That is, to give slightly more precise results. This kind of general idea that we've explained gets you almost to the borderline results, but there are completely sharp results that need a much more involved discussion. Similar concepts, but much more involved. The buzzword there is neck regions and their existence and structure. And so the last thought I want to leave you with is quantitative differentiation. It's not a magic bullet because of everything I said over here, but on the other hand, what it is a widely applicable organizing principle. And that's the basic thought that I want to leave you with. Thanks for listening.
So thank you so much, Professor Chiga, for your illuminating lecture. I'm sure that all of the audience benefited a lot from both lectures. So for the audience, if you have any questions that you want to ask, both laureates, please take this opportunity to raise them. You may type your question also.
So there are a few.
Okay, so I see here a question for Professor Bismi. So the question it says, near the end of your talk, you have mentioned one of the motivations for the hypoellipticity is to understand the relationship between the geodesics in classical mechanics and Brownian motions in stochastic analysis. However, the geodesics should be more regular than the Brownian motions, which behave like C1 half in general. Therefore, would you mind commenting how the regularity will change when the parameter B changes from 0 to infinity?
Okay, so this is a very good question. So obviously, one problem with Brownian motion is that it's extremely irregular. So the paths are continuous, but they are, they're certainly differentiable nowhere. They are almost surely nowhere differentiable. As soon as you move a parameter B from 0 to B positive, suddenly this smooths out the Brownian path. If you like, the operation is like a convolution. It's like a convolution, that is, you have a very irregular path, you make a convolution, and then it suddenly becomes regular. So, the regularity does not improve so much with time. That is, basically the irregularity scheme is essentially constant when B moves from 0 to infinity, 0 excluded. But in the limit, B equals infinity, the thing becomes totally, the speed becomes constant, and so it becomes infinity. So the reason for that is that, as I explained in my talk, for B equals 0, the speeds are totally uncorrelated. So they are allowed to fluctuate as much as you wish. When B moves to positive, they are slightly correlated. And basically, the correlation becomes stronger and stronger. So correlation here means that the mutual dependence of the speeds at different time becomes stronger and stronger. And for B equals infinity, the speeds are totally correlated. They are not allowed to fluctuate anymore. So there is not an improvement of regularity except a sudden motion from C0 or C1 half, if you like, as you wrote in your question, to C1. Yes, so that's my answer.
Okay, so may I relate this question to Professor Chiga? It says that in your talk, you mentioned about the SIMS examples in which the functions fk were introduced. What's a lesson that we should learn from these examples, fk?
So there were the SEMS examples, and then there were slightly more elaborate examples where you had a sum of those examples, but on widely separated scales. So if you look, they illustrate the phenomenon that with just a bound on the derivative, you can't say how rapidly, in terms of going down in scale, the function converges to its derivative, right? Because the region, which was determined by k, or the scale 2 to the minus k, on which after rescaling it just looks like an ordinary sine function, k could be arbitrarily big. So, I mean, of course, without a bound on, and on that region or nearby scales, I should be saying scale when I say region, it just doesn't look linear. See, and that could be arbitrarily far down in terms of scale. Below that, it does look like its derivative. But above it, it also looks like a linear function. And that was because of the factor 2 to the minus k that was in front of the bounded function sine of 2 to the k times x. So it looks like a linear function, namely the linear function 0, which is not the derivative, right? But nonetheless, it does look linear. So we have this band where it doesn't look linear, and that can occur arbitrarily far down, right? Depending on k, or 2 to the k. 2 to the k is the frequency, so high frequency, but small, correspondingly small amplitude. So it kind of shows the basic phenomenon. And then when you add examples of that type over sufficiently widely separated scales, then you see that the constant epsilon inverse is in the theorem is basically sharp. So it's just an illustration that although you don't have a bound on the second derivative, if you give up on the idea that the linear approximation has to be given by the derivative, then you still have a statement, right? Namely, there can be only so many scales, or if you like, the sum of the intervals on which it is an epsilon linear has a bound depending on epsilon, namely something times epsilon inverse. But where the scales occur, that you can't control, but you can control the sum of the lengths of the bad scales. So the examples simply illustrate how that's happening, right? So if k is very large, until you get down to scale k, it's just very well approximated by the function, which is identically 0 because of the 2 to the minus k in front, high frequency, small amplitude.
Okay, yeah, so for those who have raised the question, if you want to follow up, you can also type in chat. So I have here another question for Professor Chiga. Well, they're just wondering what sort of partial regularity results can you prove about harmonic maps using quantitative differentiation?
So as I emphasized, it's not just quantitative differentiation, but some other related ideas as well. For example, covering arguments. But the basic idea, you have to, so you, in all of the cases that I mentioned, you want to show actually in a quantitative sense, not just in the sense of Hausdorff dimension, that the singular set is small. So an example in the case of harmonic maps, so you have to start out, remember condition 1 was some sort of energy bound, or sometimes it's a bound on an energy density.
So you have to start out with that, or else you can't get anywhere. So in that case, the bound is on the norm squared of the gradient. And that's what you have to start with, or you can't get started. But what the methodology gives you is, instead of an L2 bound on the gradient, which is what you have by hypothesis, it actually gives you an LP bound for every p less than 3. And this is almost sharp. In fact, it's not quite sharp. And for that, you need this work that was much harder, sort of the second wave of these quantitative results. And that's the theory of neck regions, which was done by Aaron Neighbor. The first thing I mentioned, LP bound for every p less than 3. Aaron and I did that, but then Aaron and some younger mathematicians, Daniele Valtorta and Wenshui Zhang, did a much harder theory, more involved, that allowed you to handle borderline cases. So to give an illustration, in this case, instead of saying all p less than 3, there's a notion of what it means to be in weak L3. And the borderline case with the neck region theory gets handled by that. And in fact, it was well known that the gradient, by a simple example involving the ball, that the gradient need not be in L3. Now, the particular sharp results, that will depend on what equation you're looking at. So for example, in the case of non-collapsed Einstein manifolds, two-sided bound on the curvature, you actually, from the kind of plain vanilla quantitative differentiation ideas in the work of Neighbor and myself, you get an a priori LP bound for all p less than 2 on the curvature tensor. In that case, they showed it's a different problem. The borderline you can actually do better. They showed an a priori bound on the L2 norm. And also in this more advanced work, you get results not only on the size of the singular set, but on its structure, namely rectifiability theorems. So what we did with Aaron was, the novelty was not just the Hausdorff codimension of singular sets, but actually a bound on their size, a bound on the tubular neighborhood, the size of the tubular neighborhood, which the bound was almost sharp, where you would expect it maybe to be like the radius squared. You got the radius squared minus eta, with a constant in front that depends on eta. And then the particular border, so it's almost sharp from the plain vanilla application of these ideas. And then the borderline result will depend on the particular equation and requires a more detailed analysis. So maybe another key point.
There's another question being raised to both of Professor Bismi and Professor Chiga. This is a more general question. Yeah. So the question is the following: can the dynamics of dark energy and dark matter be simulated by relevant mathematical theories? So it's a general question.
Well, I leave it to Jeff. I mean, I saw the whole question. As far as I cannot answer that question in the form it's formulated.
Yes, the standard answer is that's above my pay grade. In other words, I have no expertise that would enable me to comment on that.
Yes.
Okay, so they was asking more about the metaverse, but I guess in principle, one always have mathematical theories, only that maybe one has to ask people more informed about the dark energy and dark matter. So Okay, there's another question for Professor Chiga. This is a question about giving examples where quantitative differentiation is actually used. Of course, you were mentioning all these results about harmonic maps and Einstein metrics and so on, but perhaps you also refer to something like computer science, and could you, I guess the person is asking more
I
technical.
can say just a little bit about that. The connection with theoretical computer science came, the problem was kind of brought to me and posed in this way by Asaf Naor. And it seems a little far from it, but maybe I can say it this way. So there was a conjecture which in theoretical computer science, which was called the Goleman's lineal conjecture. So Michel Goleman's is at MIT, and Nati Lineal is, I forget where, maybe in Israel, maybe Tel Aviv, maybe Hebrew University, I don't remember exactly. So there was a problem in theoretical computer science, which was known to be NP hard. Now, they proposed a relaxation. So instead of bounding something, they wondered if you give up a constant in what you would like to bound. You only bound a multiple, and the constant might, they hoped, be independent of the size of the problem, so that there might be an easier problem whose answer was comparable to the answer you wanted. So this is the kind of thing that occurs in theoretical computer science, and it's hard to have a feeling. So the application to theoretical computer science involved a proposed counterexample to their conjecture. And the counterexample was related to something that on the face of it seems to have little relation to theoretical computer science, but and also little relation to the examples I gave with harmonic maps and so on. But nonetheless, this was the first time where I encountered these ideas, which then got refined. And because of my other interests, it turned out that what we did could be transposed to the more geometric PDE context. So what am I talking about now? So the object, so there's an object which is very canonical, called the Heisenberg Group. Maybe everyone has heard of it. So you can think of it as, in the simplest case, 3 by 3 matrices with ones on the diagonal, upper triangular or lower triangular. So it's 3-dimensional, but it's known that it has a very interesting non-standard metric, which makes it not only homogeneous, but it also has these homotheties, which when written in coordinates, they multiply. It has 2 base directions, and then it has a center. So if you multiply the base directions by a constant and the center by a constant squared in this metric. So there's a notion of horizontal geodesics. It's a non-integrable field of 2 planes. And so you can get from one point to another because of the non-integrability, but you have to go by a longer route. You can't just go vertically to move in the center. Okay, now Naor and a theoretical computer scientist, James Lee, conjectured that you could find a counterexample to the Goleman's lineal conjecture from the following. This is a very non-standard geometry. It looks very different, even though it's very canonical from the kind of things you're used to. And the question was, can we find a bi-Lipschitz embedding of the Heisenberg group with its Carnot-Caroteo-Dori metric into this big Banach space L1. Now, among the LP spaces, L1 is exceptional. It's easier to embed in L1. In fact, from other work we had done, we knew, which was why Naor brought me the question, that you couldn't embed it, for example, in any LP space for P bigger than 1. But L1, for example, is not reflexive. And you have more room to embed it in L1. And if you could use the discrete Heisenberg group, say, given by the integer upper triangular matrices, but then scaled down by the automorphisms, the inhomogeneous scalings that I mentioned, to make something discrete. And you would, if you could prove, first of all, in a non-quantitative way, that there wasn't a bi-Lipschitz embedding, and then later which we did with Bruce Kleiner, and later with Asaf Naor, in a more quantitative way, you would have a counterexample to this conjecture. So the application was to theoretical computer science, but the analysis involved analysis and geometry, seemingly very different from harmonic maps or something like that, showing that if you have, say, a 1 Lipschitz map of this exotic space into this very big target, very flexible, still, when you got down to a small enough scale, it couldn't be bi-Lipschitz. It was going to contract points by a factor that you could control and would go to 0. So this was actually my introduction. So the connection with theoretical computer science, I've now tried to explain. It was something that was brought to me, but then Bruce and I worked on the problem and showed you couldn't embed it bi-Lipschitzly, and then we made it quantitative. And these ideas emerged in a context which I could then transpose into problems that were related to my other interests in Riemannian geometry and so on.
Thank you, Professor Chiga. So there is this question for Jean-Michel. The question was, were there more examples related to physics that you were planning to discuss?
Yes, so I would say the philosophy of the talk is in some sense the opposite, is to apply physics to mathematics. I mean, this sort of interpolation in which actually that Langevin was considering, where you need in some sense to create a mass to reflect the reality of the physical world, where the energy should be finite, is something that actually does not mean too much for a mathematician if you formulate it this way. So actually, I used it almost in the opposite way, that was to use it as a mathematical tool to prove a mathematical result, but the instrument not having specifically physical significance. In other words, the purpose was to prove mathematical results. So, for instance, just to illustrate the conservation principle, the fact that I mentioned at some point that there is part of the spectrum which doesn't change with the deformation parameter. This is typically something which appears in index theory. In index theory, you often look at quantities, you know that in principle they should depend on time, and actually you prove they don't depend on time, and this way you get the index formula in this way. That's a method of proving the index. In the case that I'm considering, in some sense, the points are replaced by the closed geodesics. And so the interpolation which is produced, while coming from the physical theory, should be thought actually as being an index theoretic interpolation, but with infinite dimensional index theorem. So in other words, the point is not to produce a new physical theory, is to exploit ideas coming from physics, to connect two kinds of objects in mathematics. Okay, I hope that I've been clear enough in that respect. So the question is not so much to explore the physical world as to explore physical techniques to understand better connections between two sorts of different mathematical objects.
So thank you, Professor Bismi, and also Professor Chiga. But time flies, and here we have to come to the end of the question and answer period. Thank you to those from the audience who raised all these interesting questions. And again, thank you both Professor Bismi and Professor Chiga to be here today and share with us. It is truly a fruitful occasion with a wonderful academic exchange. So wish you all have a good day or a lovely evening. Goodbye.
Thank you. Bye-bye. Au revoir.